Hi, everyone. Thank you for joining. My name is Steve Burke. I'm an applications engineer here at Applied Flow Technology, and today's webinar is on mastering compressors and pneumatic systems in aero. I'm going to give you a brief overview of our software with a focus on aero. We'll talk about some compressible flow concepts, the types of compressors that are out there, and which modeling approaches to use for each type. And then we'll go ahead and go through an example of sizing a compressor using aero. We'll add an intercooler to that compressor, and finally a compressor curve to that compressor. And then we'll go over how you can model reciprocating compressors in extreme as far as acoustic analysis, and then some conclusions. Some information about who we are. Applied Flow Technology has been operating for over 30 years. We're now a part of our parent company, DataCore's simulation division, along with ChemStations, for those of you chemical engineering folks who are probably familiar with ChemCAD, and we are used all around the globe in dozens of industries. Here's a look at a few of the industries where our software is used. For compressors, the most relevant industries are probably power generation, manufacturing and processing, oil and gas, HVAC, water treatment, all sorts of things. Here's an overview of our products. We basically break it down by whether they are incompressible or compressible, and whether they are steady state or fast transient. I say fast transient because we can also do slow pseudo steady state analysis using our extended time simulation modules. Additionally, we have goal seek and control modules. Both of those modules are available for aero. And then for fathom and impulse, we also have settling slurries. And for pulsation frequency analysis module, that's available for the impulse and extreme. And today's focus will be on aero, which is our compressible steady state program. So here's a very brief and simplified review of compressible flow. Compressible flow theory network solutions are based on the laws of conservation of mass, energy, and momentum. So this right here is the general energy equation you're probably familiar with for compressible flow. And this is a simple form that neglects effects of elevation changes, friction, heat transfer, any dynamic mixing between your gases, real gas effects, and so on. But these things are captured by aero. But from this energy equation and the gas equations, the basic Mach relationships can be derived, which use stagnation properties, as shown here. And as Mach goes to 1 in a pipe or at a junction restriction, sonic choking happens, which is captured by aero. And sonic choking is important since sonic choking can occur at multiple points along the same flow path. You may have noticed that that's something that isn't usually captured by manufacturer tools provided for components like relief valves. They generally assume that choking is only occurring at the relief valve and not at the piping outlet, but we can have choking at multiple places along a path. So aero has a lot of capabilities that are beyond the scope of this webinar, but I also wanted to point out a few quickly that could be relevant to your pneumatic systems. This webinar is focused on compressors, heat exchangers, and finite tanks, but other junctions include things like valves, relief valves, control valves, and check valves, even chemical separators, orifices, venturis, and more. Also, almost any component that can be represented with a loss curve can be set up in aero, which we will do later. So for types of compressors, they generally break down into two main categories. Occasionally, there are some more exotic types, electrochemical, ionic mechanisms, things like that for vacuum pumps. But the two main types are really turbo machinery, which includes your centrifugal compressors, but also your axial fans and blowers. Your positive displacement compressors are the other main category, and this can be reciprocating designs, like with a reciprocating piston or a diaphragm, or rotary designs for scroll compressors, rotary vane, screw type, things like that. So for our modeling approaches, for the turbo machinery types, you generally want to be using a compressor curve or a compressor map. Full compressor maps are really powerful, but they require more data. We won't really cover setting up full compressor maps in this webinar, but we do have another webinar that covers that. If you're interested, you can go check that out in our webinar library or our webinar YouTube's page. and that goes into the theory and how to set those up. But often you'll be using a simple compressor curve instead, which is what we'll be doing today. Again, these curves are generally appropriate for turbomachinery designs rather than positive displacement designs. So the other way you can configure your compressors is in sizing mode, and this is the most broadly applicable approach. It doesn't require you to have a pressure curve, and it can get you in the ballpark by identifying compressor performance requirements before selecting a compressor, even if you are going to be dealing with a centrifugal compressor. But basically, the outlet and inlet pressures are determined by the interaction with the broader system. And this works for also any positive displacement pumps or even the more exotic designs that I mentioned earlier. So we'll go through setting up a simple system. Here we'll just be using a pressure boundary, a tank, a compressor. At this stage, we'll just set it up with a fixed flow rate for the compressor. And then we'll be adding an intercooler, at least for the pressure loss, and a general component, which, the general component can be used for anything in your system as long as it's a passive loss, right? No active flow control valves in there or anything like that, and just single path. But this may be some machine in the system. And also we'll be setting up the pipes that connect everything. So let's go ahead and do that now. So go ahead and open Aero. And for units, I'll be using both with US defaults as my setting. And those are under these preferences here. So once you select that, go ahead and hit Start Building Model. And I always find it easier to build when I have the grid on. Let's just start dropping. Here will be our pressure. Set up the compressor. The heat exchanger is what we'll be using as an intercooler. Here's that general component. And finally, the tank. So let's set up some pipes. And if we open this pipe and choose a material, let's go down to steel ANSI. I'll use 1.5 inches. 1.5 inches right there. And I will just set this length to 10. Let's set up the rest of our pipes. I just double clicked there so I can put multiple pipes down. And I remembered the size from the previous pipe. I'll go ahead and also call this 10 feet. And I'll do the same with the other two. If we were dealing with more pipes, we would probably want to global edit these to set them up more quickly. But this is a very simple system. All right, so for the pressure junction, we can go ahead and set the elevation at 0 feet, which we'll use for this whole system. Let's just round that to 15 PSIA, that's 70 degrees. And there is no fluid currently selected, so let's go up to Analysis Setup here at the top. And we're already in the fluid panel, and we'll just use AFT standard air. So go ahead and double click on that. We can see that the pipes and junctions are also undefined. So if you click there, here's a list of the rest of the things we need to define. So we'll go through and do that now. So for the compressor, let's go ahead and put this in sizing mode for this first pass. And we'll set the sizing type to mass flow rate. And we'll be doing it in SCFM. So this is essentially a pseudo volumetric flow rate. Let's go for 300 here. Nominal efficiency. Let's set something a bit lower. First pass, we'll call it 65, and we will determine from efficiency data the compression thermodynamics. If we didn't have efficiency data, we could also, give it an estimate, which is what we did here, but we also have the isentropic and polytropic compression stages. So here's our heat exchanger. The heat exchanger, we're going to be interested in both the loss model tab and the thermal data tab here. You can also set thermal data for the pipes. So if we wanted to have these pipes be insulated or not, and wanted to have convection happening around them, cooling the pipes, we could set that up. For now, we'll leave the pipes alone. For the thermal data here, we are going to be adding some later, but let's just make it 0. So there's no heat transfer happening here. And this should be set to specified heat rate in constant. You can see we have a lot of other options where we can set it up as a cross flow, counterflow, parallel, things like that. That is more once we know what size we'll need, then we can get more specific in the modeling. But for now, we won't worry about the specific geometry. And the loss model here, we can do a K factor or resistance curve. Let's go ahead and set this one up as a resistance curve. So choose this resistance curve option here and click intercurve data. And sometimes it'll be the case that you only have one data point to go off of. And if that's the case, you can still use this resistance curve. It's a good choice. So let's say we know only that at 1 pound-mass per second, we have 10 PSI drop. 10 PSI is a pretty common rule of thumb for heat exchangers. So we can fill as quadratic. To get the other points, the curve fit order is already set to 2, which is usually what you want. So let's generate this curve fit now. And we're using air, so we didn't need to do any reference density corrections. But if you had them, they would be down here. And of course, with 3 points, it's a perfect fit. But if you had a lot of field data that you could use to get this fit, that's fine as well. All right. The general component, we'll just do a K factor. We'll call it a K factor of 10. For the tank, give us a little more pressure than the inlet. Let's call that 20 psia, and we'll just assume the temperature is 70. Since it should be flowing into the tank, this temperature won't really matter. It's only if the flow is in the other direction. It defines what it would be in this tank. All right, and we can see down here, this green light shows that everything's set up. If I click on it, I can see the analysis set up. Everything is green and good to go. So now we just need to save it before we run it. Just save it to my desktop here. And let's set up some layers as well. Let's go ahead and run it. We'll go back to the workspace. Let's set up a few layers for the compressor. The layers is down here. It's part of the quick access panel where we're changing scenarios. So let's go ahead and we can make this a new scenario. We can call this initial sizing. Then we can work off of that. And from layers, you can click the compressor here, add a new layer. I'm going to add from workspace selection since I'm worried about the compressor. Compressor. And then hovering over it, you'll see this gear here for layer settings. Go ahead and click on that. And in this label control group, click on these junction parameters here. And we want to expand to the compressor and fan summary parameters here. Let's go ahead and add mass flow rate. And we'll put that in SCFM. All right. And we'll do the stagnation pressure rise. Okay, and let's do the same thing with the heat exchanger. Doing it from workspace selection again. Just call it HX. And the junction parameters here, We can do heat exchanger summary parameters. The ones under junction parameter tabs are essentially the ones that are available for all junctions, not specific to a certain type. But let's go ahead and put the heat rate here. Go ahead and put that in kilowatts. It's a little more intuitive for me for heat rate. But that's how you would change any of the other units. And let's do the static temperatures. At the outlet, we can leave those in Fahrenheit. And in this case, these numbers are appearing right away since we already had output. If we didn't have output, they would be grayed out over here and you wouldn't see any results on the workspace since there wouldn't be any results to show yet. All right. Then let's go ahead and make one. We'll make it the other way. Blank layer for the tank. In this case, I'm going to show hide labels so I can decide what I want this to apply to. This is another way you can set things up. So here I will make the label visible for the tank. Then we'll do the general junction parameters. Let's just do the static temperature inlet down here, the temperature static inlet. Okay. We can see that this is a hot flow going into this tank. We may want this lower, which is why we have the intercooler. And we'll get to that in a second. Other things that we can look at here. Let's go ahead and see what's going on with the Mach numbers. Okay, there's no sonic choking tab up here. You can see none of these Mach numbers are going to 1. So it looks like we're not close to sonic choking. You can also check this with a profile plot. If you go over to the graph results tab, click this profile option. I will select all these pipes and look at Mach number. So you can see where it's dropping here at the compressor. And past that with friction accelerating the flow because of the change in density, you can see that the Mach number is increasing and there's a larger increase here at this general component. That's something to note about general components. If you have something there where you could model it more specifically, let's say part of your machine you have it's on a skid and you have a lot of bends and piping that you could model. Try to capture as much as you can. Because of the way this acceleration is working, you can end up getting different results if you try to, group everything into a single loss at a point versus having it distributed. Another thing to note is if you're doing something like, adding a bend specifically versus adding it using the fittings and losses tab here, the fittings and losses tab will spread that loss out across that whole pipe. So it'll be a continual effect on the friction. Whereas if you have the explicit bend, it will happen at a single point. And that can also affect sonic choking. If you have a system, maybe you put the lowest sonic CDA for the general component here, but again, there can be sonic choking at multiple points in a system. So it's usually better to use as much detail as you can. But sometimes you have a component that doesn't lend itself easily to modeling, right? Some machine or something here. And in that case, sometimes it is what it is. Or sometimes this is just something you would want to do for a first pass, and then you would want to add more detail later. And we're just getting, an estimate for what size our intercooler needs to be. So for this case, it's fine, but it's something I wanted to point out. And then in the graph results, let's go ahead and click down here to make another graph. We'll leave this as a profile graph, but this time, let's go ahead and do static pressure, static temperature, and not surprisingly for both the biggest changes at the compressor, right? Okay, so we will leave this open and come back to it. So for the intercooler modeling, we have a lot of options for how you can model heat exchangers, and that includes heat exchanger linking. And heat exchanger linking will soon work between Fathom and Aero for modeling the gas and fluid sides of a system simultaneously. So if we had a fluid cooling loop, we could do that. Also within the same model, if we had air as our coolant or anything else, we could have that in another loop and have the two heat exchangers linked to each other. We have options that are based on geometry, as I mentioned, the counterflow, crossflow, parallel, shell and tube, and then others that are based just on the thermodynamics, which are probably what you're using earlier in the design stage. So we are going to go ahead and modify it with a specified outlet temperature. Just to get an idea how much cooling we're going to need. So I'll make a new child scenario for our initial sizing. Intercooler. And let's say that the air entering, this, if it's a machine or supplying the tank, we don't want it to be at over 200. We want to see a rough estimate of how much cooling we're going to need. So now we can change this to the first option here, controlled downstream temperature. Now there's also the ability to do this with stagnation temperature. I will just do the static option, just the first one. Let's say that we don't want this to be over 200. Rerunning the model. Okay, so it looks like we would need 6.8 kilowatts of cooling from our intercooler to accomplish that. Now we can go back, get temperature profile again. And of course, it increases at the compressor and drops at the intercooler. For our last step, we will modify the compressor with compressor curve information. We'll reevaluate the performance. Another child scenario. Compressor curve. Oh. So in the compressor model section, we'll leave it as centrifugal, but we'll change it from sizing mode here to curve mode. On the left, we'll enter curve data. So let's do 0.5 pounds per second. Oh, actually, let's start 0. 0, 0.5, 1, 1.5. DP will do 22, 20, 18, 14. And for efficiency, 70, 75, 80, 70. I'm going to leave all of these on second order. And here you can see the efficiency curve in red and the pressure curve in blue. And in these tabs, we can see them with the data points. Go ahead and hit OK. Okay, go apply this. So now if we rerun, looks like the compressor is running a higher flow than we need, 357 CFM. And because of that, we're needing more cooling than our first estimate. We need 8.9 kilowatts there. Okay, and going over to graph results, we can also see now the compressor or the fan curve versus the system curve. Let's go ahead and put the mass flow units to CFM. And we'll generate this. And the operating point, of course, is here where the system curve and compressor curve are intersecting. You can get more information from it here. Let's put that in SCFM as well. Okay, so our overall efficiency is at 76.83. So it's more efficient than our first guess. So most of the increase in cooling that we need is just because the flow rate is higher. The efficiency is actually better than expected. But what if we want to run the compressor at higher speed, if we overspeed it? Let's say that we think we might need to deal with more flow in the future when we want to size a larger intercooler. Let's go ahead and create another child. 120% speed. Open the compressor properties again and go over to this variable speed tab. We can set fixed speeds, or we can have it be controlled in some way by volumetric flow rate, mass flow rate, discharge pressure, suction pressure. So if you have a VFD that's controlling to a specific parameter, that's how you'd want to set this up. But in this case, we just want to see we're running it at 120%. Maybe this is as fast as the motor we're wanting to buy can go. We will rerun that. Of course, the flow has increased significantly. It's now at 442 SCFM, and the intercooler would need to be much larger now, since we would need 23 kilowatts of cooling. However, one thing we want to look at is if we go over to this output tab and the sonic choking, now we see that there is sonic choking here at the compressor itself. So if we go to the graph, we can see this in a profile graph. Choose all pipes, and let's do Mach number. Okay, so you can see that acceleration from friction is bringing it to Mach 1 at the inlet to the compressor. Then at the outlet of the compressor where it's more dense and we have lower velocity, it's down, and then it's accelerating again as it goes on due to that friction. And we can go ahead and look at the compressor versus system curve here. I will set this to SCFM again. And we'll generate. Okay, so you can see here, this blue line is where the compressor curve was at 100% speed. And this, using affinity laws, has shifted that curve to this yellow line here. But you also notice something about the system curve. There's these inflection points. These usually happen, as is the case here, when something has started choking. And it looks like something else will choke over here as well, if we were to take the speed of the compressor further. So really, we would want the system to have a larger inlet pipe here. The rest of the pipes, when we were looking at the Mach numbers, looked like they were fine. But that's something where maybe we would make several child scenarios and figure out the minimum size that we need to keep that nice and well below Mach 1 for more efficient systems. Now, if we were not using a centrifugal compressor and we were instead designing this system to use, a reciprocating compressor with a piston design, the next step might be to do some acoustic modeling in Extreme. And we could take our aero model, load it into Extreme, and build it out from there. The reciprocating compressor options are single or double acting. We have multiple cylinders. Sometimes you can also model separate cylinders as separate junctions, either for a multi-stage compressor or just to see, the acoustic interactions within the manifold of the compressor itself. But this is Extreme only, so that would require Extreme and PFA if we were also wanting to do a frequency analysis. That's the pulsation frequency analysis module. So in the pulsation frequency analysis module, we can do natural frequency evaluation or steady state pulsation. We can also perform the steady state pulsation frequency analysis with either reciprocating compressors or any other compressor with periodic flow for your diaphragm compressors, etc. So in that case, you would set up either a cyclical transient if you can do it with the sine waves, or you would set it up just using the transient tab, but you could evaluate those. The natural frequency evaluation mode is essentially about determining the resonant frequencies of the system that could be excited by your reciprocating compressor. And because of that, the steady state pulsation mode also includes API 618 abilities. We covered this and reciprocating compressors in our previous webinar. If you want more information, go ahead and check that out. So to summarize, Aero is a steady state compressible flow software for designing and modeling your pneumatic systems. As a tool, Aero is often used to design new systems, but also for existing systems to determine upgrade feasibility, design system requirements, or to identify more efficient operating modes. 2, Aero provides detailed compressible flow modeling that captures system level interactions. The important thing to point out here is this goes beyond the simple models that are offered by component suppliers to give you a more accurate understanding of your system behavior. 3, there are a variety of compressor modeling approaches, and you can model any intercoolers your compressors may have. For the intercoolers, you can model the cooling loop as well, whether the fluid is a gas or soon if it's a liquid, using heat exchanger linking. 4, there are often several stages to the design and modeling process. Again, we have a scenario manager to make each iteration easier to deal with. Changes to one scenario will propagate to the children. So if you decide that you actually needed a different pressure for that tank at the end, for example, you could change that and it would propagate into all the rest. All right, and some other resources for you to check out. We have case studies on our website, recorded webinars, guided demonstrations. You can also request a live demonstration from our sales team or a trial, an evaluation license. And thank you all for joining. Feel free to get in contact with us, and I will open the floor to any questions here. Dave says, hey guys, thanks for running this. My version Aero 9 doesn't seem to have workspace layers. Is that something that is new or added for 10? Hi, Dave. Yes, that was added in 10. It replaced visual report. So you probably see visual report in Aero 9. Any other questions here? What is the best way to represent inlet throttling and blow-off valves for underloaded compressors? Underloaded compressors. I'm not quite sure what you mean. I'll follow up with you after this. Can you show goal seek function? Sure. So here in modules, we can just go ahead and activate GSC here. So what goal seek allows you to do is define variables and goals. So here, probably the variable you would want, let's say, since we're dealing with compressor, we want to change the compressor speed. And say we're trying to get a specific mass flow rate, trying to get it to 400 SCFM. I wonder if that sonic choking will let us get there. I should have picked a lower number. Let's say 200. Right. It's not getting us there. Maybe it's because we're starting sonically choked. Um, I would have to play around with it a bit to see what's going on in this model. But in general, basically, the GSC variables you'd see here, what speed it landed at 131%. That may have been from when we were chasing a higher flow. You can see how close we are to the goal. So in this case, we did not achieve the goal. But that's the basic idea with GSC. Another thing to note with GSC is you can have multiple variables. So, let's say you had a lot of compressors and a lot of intercoolers, and you were wanting to, change the speed of all of the compressors. You can link those variables together, and they will essentially function as one variable. You can also have multiple goals. So you're trying to get as close as possible to several different goals in your system, and that can be defined here. Goals can be defined with your junctions or in the pipes. And the numerical approach is adjustable. There's different search methods. It's possible that a different search method would have allowed this one to converge. It's also possible that it wasn't changing the flow rate because of it starting out choked. I'm not sure what's going on here, but that is adjustable. So we'd be able to troubleshoot this and find whatever speed is matching our goal. The nice thing about GSC is if you are using the variable speed option, you can control based on the pressure right at the discharge or the suction, but it has to be at the compressor itself. But really, you may be more worried about something downstream, right? Providing enough pressure in your flow to some system to keep it at a specified pressure, things like that, which you couldn't do with just using the variable speed mode by itself, but you could do by using GSC to vary the speed. Would you please share the previous webinar link? Yes, I will follow up with you after this and email those to you. What is the best way to discharge compressed air into the atmosphere and or into a piece of equipment? Yeah, so really, if we were being more accurate about this, we would want to get the exit losses here. So let's say that this K equals 1. We can go ahead, do the same thing on the side flow into the pipe. Entrance loss 0.5. So that's how you would add those. You can also model the outlets if you have an exit orifice, a screen, spray discharge. There's a few different ways you can do the outlets. If you have one of those junctions and you want to use it as an outlet, the thing to note is this exit option here. That would allow us to define the exit pressure and exit temperature. So now you can see up here, it is only expecting one upstream pipe. So that can be used as a boundary condition now. Can Aero do transient analysis? Yeah, so in XTS, you can do transient analysis. One thing to note here, just another child. Is it will affect our heat exchanger modeling. And with this heat exchanger, yeah, the heat transfer is not going to be modeled now. That's not a limitation if you're doing fast transient analysis in extreme, but it is something to note if you're doing XTS. So a system like this with an intercooler, it wouldn't be ideal to use XTS. But if you didn't have an intercooler and you wanted to have, some assigned flow over here, that's taking air out of this tank and it's varying over time and you're trying to maintain a specific pressure in that tank. That's something you could do with XTS. You could actually combine several modules at once. So for example, if you were trying to maintain a specific pressure here by varying the pump speed, you could use GSC and XTS at the same time. So you do have some flexibility. Just be aware of the heat transfer situation. Carly says, I utilize compressed air to keep equipment clean from dust and moisture, etc. Ron says, how do you link with Fathom? So the Fathom linking is actually in Aero 11 and Fathom 14, which I'm unable to show yet. But I can give you a call after this and show you one-on-one. Graph results show the static temperature decreasing along the pipe from the intercooler to the tank. However, it looked like the workspace results for the tank show the temperature above that of the intercooler outlet. Is there a setting that's causing this discrepancy? Yeah, so that's not because of a setting. Basically, what's happening. So like this being 205 degrees and this being 200 degrees, the reason that is because of the energy equation. So the stagnation enthalpy is staying constant here, but because it's a real gas and not an ideal gas, the temperature is actually changing because we have the density changing as a result of that pressure loss. So because of the friction, we don't have quite the same temperature, but in an ideal gas, you would be correct. You would expect to see the same temperature there. And that's why the equations I showed earlier were a little misleading, because again, those are a simplification of what's going on. But yeah, we can see here that the stagnation at the outlet from the heat exchanger here is at 227.7 BTUs per pound mass. And we're seeing the same thing once it's going into the tank here. So that is what we're expecting to stay constant for that conservation of energy, and we're seeing that it is constant. Another person asked for a web link for the reciprocating compressor webinar. Yes, I will follow up with you after this. Dryers are considered. So if you were modeling a dryer, yeah, you'd probably want to do that as a general component. Another thing you could do is you could do it with a gas mixture. Oh. So in Kimpack or Ref Prop, you can do dynamic mixing. So maybe you would have some mixture with water vapor here. Oh, let me do this in Ref Prop. Oh, I bet I have to search Steam. Oh, here we go. And then you would just want to add dry air. And then here, I'm not setting it up as a mixture, but just showing you how you do that there. And you would want to use this separator here for any mass that's leaving the system. So I can morph this general component into a separator. Well, I need to set up the mixture in detail, but essentially you would have some mass flow of a given part of the mixture. The steam in this case would be pulled out of that, and you would have just the air downstream. We have the same Goldstein function for fathom. Yes, we do. Filling a tank with a gas increases the gas temperature inside the tank because of the work being done on the gas. Does Aero software capture this phenomenon? Yes, it does. So in this case, that tank was being modeled as an infinite tank because it was a purely steady state model. So it wouldn't be changing in temperature over time. But yes, if we were using XTS and modeling that as a finite tank, it would be affecting the temperature over time. Another person asked about dryers, which we discussed. Can you use assigned pressures for the outlets? Yes. Yes, we could use assigned pressures as well. We could also, in some cases, use assigned flow. In this case, it would cause conflicts during the sizing mode since we were specifying flow. So there'd be a reference pressure error in between the two. But yes, in some cases, you'd be using a assigned flow as well for a boundary condition. Is there a snubber sizing capability for reciprocating compressors? I don't believe so, but I'm not sure what you mean. Are you using static temperature? Is there any difference? Yeah, so they are going to be quite a bit different. Yeah, because of this relationship. So the closer that you get to Mach equals 1, those are going to be different. We were just using static temperature because that's usually what you're measuring if you have thermocouples. But yeah, you could use stagnation temperature if you'd like. What's the minimum pressure drop required through the air control valve to achieve good control? I believe you usually want them about 70% open. I'm not sure what the specific pressure drop would be. It would depend on the valve and the system. I should note that control valves, we can model them as failing. So if you wanted to see what happens when they fail to control and what state the system ends up as, you can model that. Can XTS help size air receivers in line tanks to absorb usage swings? Yes. Yes, it can. Also, if it's not for usage swings, it's for pressure waves, as far as the fast transients, or for damping the acoustics. If you were doing a reciprocating compressor analysis, that you would do in AFT Extreme. Static temperature, does this mean the temperature in the steady state condition? No, the static temperature is essentially the actual temperature. The stagnation temperature is, if you imagine the tip of a wing, where the flow stagnates at the very tip of the wing, it's hotter than it is in the bulk flow. That's stagnation temperature. My end goal is sizing orifices, but there by any chance a webinar out there specifically for sizing orifices and aero? Yes, I believe there is. But the general approach for that is you would set up a system with a control valve there for whatever flow or whatever pressure you're trying to achieve. And then you can see the equivalent CDA that you would need for the orifice and size the orifice that way. Of course, you could also do it with the GSC module if you're wanting to do something that you couldn't capture using a control valve. Could I use the separator tool to model an existing compressor system in the field and to estimate water dropout from intercoolers or aftercoolers in my compressor system? As far as water dropout from them condensing, no. Well, you could if you put it upstream of the heat exchanger, but you would have to know the mass flow rate that the water is leaving the system. So you would already have to assume that, but maybe you could calibrate it with other field data. You might be able to do it indirectly, but it would depend on what data you have. Can we use variable speed for positive displacement compressor? That's a good question. I think as far as the affinity laws, you wouldn't be able to, because the affinity laws are for centrifugal compressors. So the relationships between speed and the pressure and the flow and the power, those correlations are intended for centrifugal, but yeah, well, so not the speed directly, but you could scale, the flow rate itself, since it's going to be tied to the speed. Yeah, I think that's essentially how you would do it, but it wouldn't be using the variable speed tab. It would just be, setting this to, oh, this was supposed to be SCFM. Oh, well, yeah, it would just be setting this to, 600 if you wanted to double the speed or anything like that. All right, that looks like it's all the questions for now. Again, I'll follow up with some of y'all after this, but thank you again for joining.